This meeting is being recorded.
it goes, sorry, say it one more time. This thing. Oh, the zoom pointer. Oh, wow. Oh, so I should try to use that one. I should try to use this one because everyone can see it. Okay. Thank you. GPT.
All right. Welcome to the second day. We are very happy to start off with Jim Harvison from Northeastern, who will talk about machine learning in the string landscape.
Right. Hello, everyone. Is the mic okay? Where's it a little? Oh, okay, good. Yeah, I guess I can speak loudly enough over this beautiful music. That's fine. It's really not a big deal. As long as we have beautiful music, we might as well have a beautiful painting, right? My secret hobby is that I'm an oil painter, and I slaved over this for a very long. This is no. I'm kidding. This maybe while we're getting set up. Good. I think we're good. So I'll tell you at the outset that this is actually a product of GPT-4. So I have my $20 a month GPT-4 account, and I said something to the effect of, give me an image of Paris, make string theory and machine learning be a part of the game. So this stuff, this sort of garbage in here is its interpretation of neural networks and string theory or something like that. And it gave me some very clean images. I said, no, make it impressionist. This is what it came up with. So, one of the things that we get to grapple with is how are we supposed to think about this very powerful tech in the context of science? And that's a little bit of one of the things that this talk is about. But before that, let me first of all thank the organizers for the wonderful invitation. It's kind of seldom that I see this many people together in a room for a meeting that isn't one of the big yearly conferences. So it's just a testament to the effort you guys put in to get so many wonderful people here. So I'm going to tell you a little bit about some of the things that's been happening in the machine learning corner of string phenomenology the last few years. And that is a little bit separate from some of the things that we talk about at String Data, which is our yearly meeting. People are doing increasingly broad things, and I'm going to try to focus on the string theory aspects today. But first, let me tell you a little bit, if you want to connect in this area, there's a couple of ways to do that. First of all, I am pleased to be a part of the NSF AI Institute for Artificial Intelligence and Fundamental Interactions, where we want to advance physics knowledge from the smallest building blocks of nature to the largest structures in the universe, and hopefully in the process to galvanize AI research. This is a Boston area NSF-supported institute, MIT, Harvard, Northeastern, and Tufts, and we do a lot of different things. We're about 150 people in total when you consider faculty and postdocs and students. So you can check out our website and our seminars and our colloquia and our summer schools and workshops and so forth. We have a couple of postdoc offerings at Northeastern this year that I am shamelessly advertising. Some of them are in connections with ML, if you like this talk, but there's also some that Fabian Rula and Sarah Harrison have that don't necessarily need to involve ML. So if you're interested, please apply. And finally, there's a couple of upcoming meetings in the next 6 weeks, actually. So if you've been looking for something over the holidays, consider coming to Caltech. There's a machine learning and math meeting in a few weeks there that is followed immediately by String Data 2023. That's like 10 days before Christmas. And then in the middle of January, we have strings, fields, and deep learning at the Aspen Center for Physics. The meetings look very exciting. There are a couple of more spots if people want to join, so definitely send me an email. OK. So the necessary motivation, in the back of my mind at least, is that string theory and quantum gravity are hard. This does not need any introduction to this audience. But given that they're hard, there's a question that's fun to do in a meeting or to potentially discuss over a few beers with friends, which is if you let yourself ignore the hardness for a moment and just ask, what would we want to do in principle if we weren't concerned about the hardness of the theory and just said, what is it we want to do? This is something that in computer science you might consider being asking an oracle. So when people talk about complexity theory, they might ask, how many oracle calls do you get to make, and so on and so forth. And basically the idea is that the oracle is like some all-powerful being that is able to answer any question that you ask it. And so in that context, what in principle would we want to ask about string theory and quantum gravity? So a couple of things that you might ask if you didn't worry about hardness, and you're going to laugh a little bit when I write these things down. You might want to ask the oracle, what is the complete non-perturbative definition of M theory? That this is something that really, to get where we want to in the long run, having better non-perturbative formal control over the theory is something we like. But if the oracle and the one rule of this game is that you're not just allowed to ask the oracle, is string theory correct? It's like, you need to do a little bit better than that. So first you'd want to ask, what is the complete non-perturbative definition of M theory? Then you'd want to say, pardon me? Yeah. I actually don't know any French, so I have no clue whether that's funny or not. But what does this say? Huh? Replace the lamp. That's a very interesting. Yeah. Okay. Good. I don't know. Very good. So if you knew a complete non-perturbative definition of M theory, and you could ask the oracle, you would say, what are all of the decay? What are all of the vacua? And not only that, I want to know all of the decay rates of all of the vacua, and I want to know the decay. I want to know the branching ratios from vacuum I into vacuum J, and so on and so forth. And again, this is supposed to be laughably complicated because we know how hard it would be to get this information, but the oracle doesn't care because the oracle can provide it. And then you might ask, what is the way to think about the cosmological measure or some other measure that you're interested in for some reason? And then you might ask something like, sorry, how do you make, given this sort of setup where you know all of the information about all of the vacua and you know the cosmological measure, then it's still hard to make statistical predictions because these calculations are big and complicated. So at many places along this story, maybe not as much here, there's just concrete computational questions. But if this is a dream that feels very unattainable, maybe 2 points come out of it very clearly. One is that we need formal theory. There's just no way around it. But given that list that we want to know as much about all of the vacua as we can, and then we want to understand how they decay from one to another, and we want to understand statistics and so forth, I think even though we need formal theory, there's no question that we just need smart computation. And so that's part of the setup for how I think about why I'm doing ML in this context and why the community is interested in it, that we need formal theory. And I think clearly at the end of the day, we're also going to need computation. Okay, that's probably not that controversial. So we've been doing this for a little while. A few caveats and comments from the modern era of thinking about machine learning and string theory together. First of all, a number of string pheno folks are working on ML, and they have interesting non-string pheno offshoots. I will cite some references, but interesting works that have nothing to do with string theory, I'm generally not going to talk much about today. Using large language models for research, ML or otherwise, is very cool and interesting. It's something that I sometimes do in my own research. I implement these things in my class. That is an exciting topic that's worth a talk of its own. I won't talk about it here. Feel free to ask me questions, either in the Q&A or afterwards. To those working in this area, replace the lamp. My sincere apologies if I didn't adequately cite, cover, or present your work. I tried pretty hard, but there's clearly some things that I'm going to miss. And if you'd like, please raise your exciting results in Q&A. But if you do that, please do it briefly so that it doesn't totally dominate the conversation. Another comment is that increasingly we're thinking about statistics in more sophisticated ways. I will use some statistics language throughout this talk, like sampling and drawn from, which might sound gross, but the fact of the matter is that if you have ever done a computation in an actual string compactification, you yourself have sampled string data, whether you like it or not, because you picked your Calabi-Yau somehow and you wrote it down to be able to do your computations. So even though statistics is not the natural language of our field, I think that some of these things are inevitably happening behind the scenes, and we need to think a little bit harder about that. And finally, Some numerical techniques can be rigorous. Rigor is a loaded term I have learned recently in some discussions. So what I mean by rigor is what you presumably mean by rigor, which is results that have zero error. In some other communities that use ML and physics, they're perfectly happy to allow for statistical convergence. So lattice field theorists in the infinite data limit do exactly converge to the right distribution that they're trying to draw their lattice field configurations from, defined by the action. But I don't mean statistical convergence. I really mean zero error results. So in this context, you can either think of that in the context of applying ML and making it rigorous, or using ML theory. Okay. Very good. Okay, so the outline is as follows. First, I need to give you some machine learning preliminaries. I'm going to tell you about neural networks. I'm going to tell you why neural networks are strong. It's due to something called the universal approximation theorem. But the universal approximation theorem is why they're strong, but it doesn't help you find the neural network that is the good approximator of the function you're trying to approximate. For that, you need wise architectures, which is about how you stitch together small functions into big functions in a way that makes sense based on your data. And then I'll talk about some famous examples and some verbs that help you understand the different types of machine learning out there. Then I'll run through a section of the talk that I call cursory glances. In the end, this section and the next one aren't quite so different. These are going to be shorter looks at some things that are happening. I'm going to tell you about prediction problems in string theory associated with supervised learning. I'm going to tell you about some cases where you can be rigorous, where you can generate some conjectures and prove some theorems. I'll tell you about structure in data coming from something called persistent homology. I'll tell you about search problems and how you might do them in string theory with reinforcement learning, genetic algorithms, and quantum annealers. And then I'll pass to a part of the talk that I'm calling in-depth looks, where I will tell you why you might want to auto-differentiate everything. And I'll tell you about some recent work in this context for flux vacua. And then finally, I'll talk about some flows. Namely, Magdalena is going to give a great talk next on Calabi-Yau-metrics, and I'll tell you about some mathematical ways of thinking what's happening associated with those geometric flows, motivated by some recent results in neural network theory. And if I have time at the end, I'll tell you about generative models and simulating string theory and statistical inference. I have a lot of slides. I'm not sure if I'll get here, so I guess if I don't get there, I'll just have to give up on my dreams and still move forward. So very good. OK, so this is the outline. I should encourage you, please interrupt me at any point. I'm happy to take questions throughout. But I guess at this point, there probably aren't any. OK, so preliminaries. Let me tell you about neural networks, about universal approximation, and also about architectures. I will then give you some famous examples and their associated verbs. I think sometimes when you talk to computer scientists or you hear it in the news, a neural network is posed as something that sounds much more complicated than it is. I think for our community that likes to think mathematically, we can just think of a neural network as a parametrized function. So it's just some function with some parameters in it. It is typically a big function. We normally don't describe functions by words like big or small necessarily. But by big function, I mean a function that is composed out of many other simpler functions with many parameters. That at its essence, basically every neural network architecture that you've heard about is some sort of parameterized function that is big and composed out of simpler things. These neural networks have many parameters in them. In modern incarnations, it's something like billions. And therefore, you can think with these parameters as there's some sort of parameter space. Those parameters get stuck into the function. And therefore, what the neural network is doing is inducing some sort of map from parameter space to function space. Typically, when you started on your computer, those parameters come from somewhere. They're drawn from some parameter distribution P of theta when you initialize your computer. And that parameter distribution affects the statistics of the neural networks. If you'd like, you can think of the choice of this parameter density on the parameters as effectively putting statistics on the function space associated to the neural network, precisely because the neural network is a map from parameter space to function space. So if you'd like, this defines a field theory, and that's something that I've been interested in recently. But that is not the subject of this talk. So this is the simplest example. This is Rosenblatt 1954 or something like that. This is something called the perceptron. F of x, I promised you, it is a function. These w's and b's, w's are matrices and b's are vectors. Those are the parameters. I promised you parameters. So this is a parametrized function. Good. This is something called an affine input layer. Sigma is an element-wise nonlinearity. And this is an affine transformation to output that defines this thing called the perceptron. And basically, the most vanilla type of deep neural network that people study is basically compositions of this thing that just compose it more and more times with itself. I also promised you that parameters are drawn from some distribution in it, and this is a typical choice here, where n is the normal distribution. So a neural network is a parameterized function. That doesn't get us very far unless there's some reason to think that those parameterized functions might be useful for something. And that's where these universal approximation theorems come in. So these multi-layer perceptrons, which is Rosenblatt 1958, actually, this is the architecture I just told you about. They're universal approximators, which basically means that they can, with some certain assumptions attached, approximate any function. And the error is of order 1 over n. So if we talk about the approximation, we want to say how bad is the error from the ground truth. And it's 1 over n, where n is the width of the neural network. So just for context, this direction here, or alternatively the dimension of this vector in here, is called the width. You can make the width big by making the neural network big and the parameters big. And in that limit, you're going to get better and better and better approximations to any arbitrary function. There are different versions of this, like many famous theorems in sort of stats and computer science. There's sort of different versions on the same thing. And so for that, I encourage you to read up. Yeah. Pardon me? This is neither. I haven't talked about training yet. This is the question in the function space associated with the neural network. Is there a function somewhere that can approximate any arbitrary function? And so I haven't talked about training yet, which is a very good point, because the existence of such a function in the function space does not mean that it's easy to find. And that's why training is non-trivial. Yeah, good question. Thanks for interrupting, and please keep it up. Good. So on the other hand, this is why they're powerful. But because you have this, it means that somewhere in the function space, you can, in principle, approximate any function. But it doesn't mean that you can actually figure out what that function is. So what we do in practice is we come up with clever architectures, is the phrase. An architecture is how you stitch the simple functions into complex ones. So for example, the architecture here in this previous example is this one. And that's the feed-forward neural network. But there's others. So for example, a convolutional neural network is something that works very well on image data, because image data has local features. And you could train a convolutional network to identify the Eiffel Tower. And in this case, it would pick off this local feature using a convolutional kernel. The transformer, which you've heard a lot about recently in the context of GPT, because that's the T in GPT, is something that works very well with language data. That can be much broader than you might think, because, for example, word problems in group theory, for example, associated with the braid group, are very naturally thought of as language, and you can apply these techniques there. But in any given problem, the sort of question that you want to ask is, what is the structure of my data? What am I trying to do with it? And how do I choose my architecture such that I might succeed as well as possible on my problem? So even though we have universal approximation in these very simple models, in principle, in practice, it's hard to find the good approximations. And so we choose architectures to make our lives easier. OK, so here's some famous examples. This is a database called MNIST. This is supervised learning, where you learn to predict, given one of these little images, you learn to predict whether it's a 2 or a 9 or so forth. So supervised learning is about labeled data, where each little image here has a label, 9, 8, 4, 2, 7, et cetera, associated with it, and you learn to predict. Good. So some of my slides might be a little off due to some last-minute changes. So this is AlphaZero down here. AlphaZero and AlphaGo are a very famous example where you use reinforcement learning to search or play. And these are the world's best at chess, Go, and shogi right now. Of course, I have to talk about generative models. Generative models are about generating or simulating data. In this example, this was a text-to-image generative model. I gave GPT-4 some prompts, and I played with it for 5 or 10 minutes to look at various different examples. I said Paris, string theory, impressionism, neural networks, et cetera, and this is what it came up with. And there's I'd be happy to give examples of ways in which there's huge failure modes where things are obviously wrong, not necessarily with this image, but with other images that are like it. But at the same time, we should really be pretty impressed that you can get this sort of thing out from text. So it's generating or simulating data. And finally, there's also text-to-text generative models. So I wanted some sort of haiku based on this conference. And it said, in Paris, threads weave, string theories, vast landscape, Eiffel echoes deep. But if you actually count, this is not 575. This is actually 565 associated with the haiku. So it got something slightly wrong. But nonetheless, these are very famous examples that are out there that demonstrate the power of these models. And something that increasingly large numbers of people are interested in is, given the power of this sort of stuff, how can we use it for science? Okay. Any questions before the next part of the talk? That's just the backdrop. Okay. All right. So I'm going to give you some cursory glances at some various works that are out there in this community. So first of all, and in the process, I'll tell you some more details about some of these machine learning techniques. Some of the early string and ML papers were using something that's called supervised learning. I won't cover too many of the results from this work, but I want to tell you about the basic setup because it's the most essential type of machine learning. The data here is a set of input-output pairs. So it could be some polytope and some property of the polytope. It could be an image and the label associated with the image. Is it a hot dog or not, for instance? And given that data, the input-output pairs, the basic idea is that you want some sort of parameterized model, f of theta, that is going to make predictions given some element of x. And you want to see how well that prediction compares to the ground truth label y that you have. So in this context, you have something called a loss function that takes two elements of y and gives you some real number that tells you about the goodness of fit. So for example, in linear regression, we typically do mean squared error that says, given my line that is my parameterized model, I go through all the data points and I see how well the line fits the data points, and I add up the square errors, and that's some notion of how good the fit of the line is. But given a line that fits really badly in linear regression is the simplest supervised learning. Basically what you do is you do some sort of optimization on theta to try to minimize L on the data, for example, via gradient descent. So if y is mx plus b, you want it to run through the data, and you just optimize m and b to be able to fit it. So that is supervised learning. Something that is interesting about supervised learning, which was sort of my first bit of interest in this context. This is how I got into it. Hold on. Nope, too far. Okay, good. This was one of the things that from this paper that we wrote a few years ago that I still think is really interesting. Is the idea of doing something that we called conjecture generation, where you get rigorous results out of ML and not just numerical ones. The basic idea that we had is to use any ML algorithm, supervised or otherwise, on some interesting problem. Then depending on the details, you might imagine that there's some way to open the box to identify some sort of key decision variable. And then based on that decision variable, you could bring in some human expertise. In the context of this problem, it was an F-theory problem, so I was someone that had some expertise there. And bringing the human in, you might be able to see the decision variable that's crucial to making the decision about what the ML model is predicting. And then it might suggest some sort of conjecture that you might iterate and you might prove a theorem. So in this particular context, we were interested in how visible-like sectors might arise in a particularly large ensemble of F-theory geometries. There was some crucial decision variable that was appearing with probability like 1 out of 200 or 500 or something like that, associated to E6 grand unification. And we were able to prove a theorem about this. So this can maybe be taken with a grain of salt. But this idea is an interesting idea generally that some other people have been doing as well in our community. So for example, Andre and company studied line bundle cohomology, dimensions of line bundle cohomology in various setups. And you can see some of the results here. It was observed recently that line bundle cohomology has been described by dividing the Picard lattice into certain regions. Sorry, it's a little small. In each of those regions, the cohomology dimension is predicted by a polynomial formula. So in particular, when you divide up PIC in these contexts, you find that there's piecewise polynomial descriptions that are good models for the cohomology dimension. And in various cases, they were able to take this, I mean, both from a numerical perspective and from a math perspective, this is the right sort of structure that emerges. And they were able to study examples where they proved some theorems about the structure of those piecewise polynomials, Hodge numbers. Similarly, a group connected with the Penn group and elsewhere was studying line bundle cohomology and associated jumps in F-theory. They were interested in studying vector-like Higgs pairs that are arising in 4D F-theory models for phenomenological reasons. And they white-boxed the machine learning approach that provided some intuition for jumps that were due to curve splittings, jumps in the cohomology that were associated with new vector-like pairs appearing on subloci in moduli space. So this was ML-inspired intuition for vector pairs. A famous result from 2021 that I can't help but mention, maybe this is the one really non-string theory result from the talk. There's a DeepMind paper from 2021 that did conjecture generation in the context of knot theory. And basically, one thing that they were asking, given some knot and some associated topological invariants, like the hyperbolic volume, like the signature, like the Jones polynomial, et cetera, they were interested in the question, can you predict the knot signature from the geometric invariants? So if I have a bunch of knots, and I compute a bunch of topological invariants, and then I want to ask, if I don't feed it the signature, can I predict the signature accurately given those other ones? This was something that they were able to eventually prove a theorem about. And the way that they did it was they trained a neural network F, and they did something called gradient saliency. So these X's here are these various topological invariants here that are appearing on the left. And basically what they were asking is for the gradient saliency of any individual feature at input, any individual topological invariant, they're basically asking how much does the prediction of the network change if you vary one of the topological invariants at input a little bit. And this very simple analysis, asking about the response of the neural network to a fluctuation in one of the topological invariants, gives you this graph that tells you that some of the topological invariants are much more important than the others, and some of them almost don't matter at all. So that's the sort of result that can come out of this numerical algorithm, that when you bring in a team of knot theorists and then you give them this data, and then they start thinking hard about how these topological invariants are related to the knot signature, they can end up writing down a conjecture and proving a theorem. And so this is the theorem that they proved in this Nature paper. They also have some representation theory results, but this is a great example in ML for math of how they took some honest-to-God numerical techniques that had error, that were not always correct. They have this way of opening up the box and understanding what's happening, and based on that, they have a theorem that they didn't have before. So, so this is their results in the context of knot theory. No. Yeah, that's a great question. So there's all sorts of different techniques one might do other than this. There's something called layer-wise relevance propagation. Then there's simple things like just use a decision tree. Apparently, there's some skepticism about the breadth of applicability of gradient saliency techniques in the ML community. I haven't followed that closely. In this case, it worked. But in general, these sorts of things are considered to be brittle, and you need to be careful when you're using them. Yes, that's true. That's absolutely true. That would be one failure mode. They didn't have that in this case, but you can find machine learning literature expressing both excitement and skepticism about these sorts of ideas. And in any given example, the question is, did it work? Good. Another thing that you can ask, this was about sort of getting rigor out. Another thing that you ask is about the structure of data. And I would like to, before talking about the details of persistent homology, I'd just like to get at the idea, first of all, that sometimes when we talk about data, we have a data manifold. And even if we don't have a data manifold, we might have a data topological space, right? So I'm just imagining that I have a data manifold M that's in some ambient space A. For example, in this community, we think about Calabi-Yau and ambient spaces all of the time. Alternatively, OK, not a manifold, but you could think about the space of stabilized vacua in moduli space, the space of flux vacua, and we'll see an example of that in a second. And given that data manifold, M in general has geometry, topology, et cetera. And if you want to understand your problem, you'd better understand the geometry and topology of that space. But a problem arises when you remember that whether you're picking your favorite Calabi-Yau or picking your favorite 100 Calabi-Yaus, we are always sort of sampling from the data manifold. In no case in string theory, generally speaking, are we able to understand and control the entirety of the data manifold. We do samples, period. That's what we do. And given those samples, X's drawn from some density, some probability density on the data manifold, what you would get is some sort of point cloud in the ambient space. And you want to ask the question, how can I recover the information about the topology and or geometry of that space, the fundamental thing, if I only know samples? So in this particular case, I have 3 examples of 10 samples, 50 samples, and this should be like 100 or 250 samples from the annulus. In this case, 10 samples doesn't look like the annulus at all. In this case, it's starting to look more and more annulus-like. And at this point, I have enough samples that it's very clearly an annulus. So in the context of a scientific application or string theory, there's questions of if we only take a few samples, what sorts of things are really there that we might miss because we only had a finite number of examples? What structure is really there that we want to uncover from samples? Fortunately, mathematicians, okay, so in the context of if you knew M itself, you would ask about the Hodge numbers and the topology and homology and so forth. But if you only had the samples, you'd ask, how would I recover information about the topology of M given only those samples? So mathematicians, I think it's 20 or 30 years old, Gary knows a lot more about the history than I do, came up with persistent homology. Persistent homology is the idea that you have a one-parameter family of simplicial complexes that yields homology families HK. The HK depends on the samples and some filtration parameter T. The simplest version of this is something called the Vietoris-Rips complex. Basically, the Vietoris-Rips complex is formed as follows. First of all, it depends on delta. And to each k-point subset of the samples that are within a delta ball of each other, you can study those things, you want to add a k-1 simplex to the simplicial complex. So this is an example of the Vietoris-Rips complex being applied to this particular point cloud. And you can see certain triangles, edges, and tetrahedra appearing. And given that simplicial complex, you can talk about its homology. So this is an algorithm given a parameter delta and a set of samples to write down a simplicial complex and talk about its homology. The basic idea there is that the homology and the Hodge numbers will jump as a function of this filtration parameter delta. That is, sometimes a cycle will be born where there's some jump up in the homology as you increase delta, and sometimes a cycle will die. So in the context of the annulus, here, if delta is super small, if delta is like epsilon, this is just 10 disconnected points still, 10 disconnected little balls. H0 is 10, H1 is 0. But as you make this delta bigger and bigger, these things eventually start to merge. And let's do it on this data set, actually. As they merge more and more, eventually you'll be able to go around here. And then at some point, delta becomes so big that the interior here gets filled in, and H1 drops back down, and the one cycle dies. Okay? This is this beautiful idea. I think it's natural, given that we're always working with samples. And so that's what people have been applying in the context of string theory. So that's persistent homology. It's very natural. It's just a one-parameter family of homology theories that you apply to some data set to uncover the structure of the theory. So in the context of, there's a couple of works in the context of string theory that do this. This is one of Gary's. Yeah, sure. Yep. Yeah, so in the example I'm going to get to in a second, it's not a priori clear what the underlying data manifold is. In this case, it's obvious what it is, and I'm just trying to develop the numerical techniques that can recover the fact that this is clearly an annulus, right? This is drawing from a... Yeah, you can, for example, fluxes. Yeah, for example, fluxes. And so if you don't know about the underlying structure that you're drawing your data from, if there's some mystery, you might ask, given the data, how can I understand the topology? So this is just an example. If you didn't know what an annulus was and you were just handed this, clearly there's something going on here where there's a direction. But in this version, I mean, if you make the marker size small enough, there's simply no overlap. It's just a collection of points. But it's a collection of points that somehow is arranged very nicely into a circle. And you'd like numerical techniques that can address that. Exactly. Good. All right. Very good. So Gary did this in the context of a flux vacua. So these are 2B flux vacua on the rigid Calabi-Yau and the associated axiodilaton values. And for the different flux vacua here, there's very clearly circles and voids here that are actually appearing in the actual string theoretic data that you would like to be able to uncover and understand. This is some work that Gary and Kira Chifi pioneered a few years ago. Realize I'm running very slow on time. Yeah, okay. I'm a little bit behind, so I'm gonna keep going. But so that's the idea of persistent homology. It is being applied in string theory in very nice contexts, and it uncovers the structure of the data. Something else you might want to do is search. One way to do that is via something called reinforcement learning. The key idea is to win the game, and that's an exact solution to the problem. There's zero error. The basic idea is that you have some agent here that interacts with an environment. It perceives a state from state space, and given a state in state space, you want some sort of policy function pi that gives you, given a state, gives you an action that you should take. It picks an action given the state. In the process, it receives a reward. The successive rewards can accumulate into something that's called the return. And there's various statistical ways to measure the value of the state based on studying how much reward you would get if an agent started from that state over and over again and experienced many trajectories through state space. So this is the subject of reinforcement learning. This is the subject where these famous examples in chess and Go come from. They're trying to search for something. In the case of Go and chess, they're trying to search for a winning state where they beat their opponent. So this was something that we got interested in a few years ago. We applied it to type 2A compactifications with intersecting D6 branes. Two things to note about this plot is that the agent learns, TC is tadpole cancellation, add the K and you get K-theory constraints, and add the S and you get SUSY constraints. As it learns more and more on this axis, there's sort of these punctuated equilibria where it gets stuck for a while, and then there's this jump and it learns how to satisfy the SUSY condition. One thing that's important to know about this is that these games, because you can roll out the agent, you can see trajectories through state space that it plays as it does more and more. You can study the statistics of what it does and see if it's learning particular types of strategies that you can actually understand. So in the context of chess, it learns openings that grandmasters have come up with. It also learns strategies that grandmasters typically don't play. In the context of type 2A compactifications, there's this thing that is called using filler branes to try to sop up the tadpole. And this is actually something that the agent did in a particular iteration of the game, where it was learning a strategy that humans had come up with prior. There's other ways that we do search in string theory and others with genetic algorithms, where we simulate natural selection by evolving solutions using mutation, crossover, and selection. Of course, when you do that, and at every stage, there's some sort of survival of the fittest. We have some new child of strong parents that is presumably strong, and then you get rid of the weaklings. There's also something called quantum annealers that uses quantum tunneling on something called D-wave hardware that does some sort of search problem of various hard optimization problems in physics. So here's some very early work in these directions from many years ago from Fernando and Steve Abel. In a more modern context, I really like the title of this paper. This is Andre and company, Decoding Nature with Nature's Tools, Heterotic Line Bundle Models of Particle Physics with Genetic Algorithms and Quantum Annealing. One of the things as we do more and more search problems in string theory with these techniques, is we want to try to compare and contrast the different things that are out there. So for example, this is about genetic algorithms and quantum annealing. There's also a number of works comparing genetic algorithms with reinforcement learning. But the basic idea is that these things are good for search. So the setup is heterotic E8 times E8 plus physics constraints, anomaly cancellation, spectrum, polystability, et cetera. And you'll notice that in some given Calabi-Yau, the genetic algorithm and the systematic scan, the genetic algorithm is finding all of the solutions, all but one of the solutions. This is the percent found. And as you use the genetic algorithm to search the space and find the solutions that satisfy physics constraints, you want to ask what percent of the systematic scan solutions has it found, but crucially, what percentage of the state space did it explore? These systematic scans, as we know, are very costly to scan over tons of stuff. And so you want some sort of algorithm that can do it more intelligently, and then you want to ask how many states did you actually see? So like in this case, for this particular manifold, it found all 38 of the solutions that the systematic scan did, but the fraction of the state space that it explored relative to that was 10 to the minus 14. And of course, our gracious hosts have a beautiful paper on using genetic algorithms to look for flux solutions in the context of, I think it was M theory on K3 times K3, in the context of the tadpole conjecture. And the results that they got with genetic algorithms support the tadpole conjecture. Finally, Harold is here. And if you're interested in string field theory and ML, you can ask him about that. He used neural networks to try to distinguish the vertex and Feynman regions in string field theory, which are relevant to characterizing properties of connected 4-point functions. Okay, very good. I've got 20 minutes left. Any questions on the cursory glances? Sure. So, good. Flux sampling in the context of real value things versus discrete value things that need to satisfy strong arithmetic constraints. Good. Yeah. So Andreas is raising his head because he wrote a flux sampling paper very recently on. Did you guys sampled discrete fluxes and found solutions, right? You're pointing out something a little more general, that in many times we mock up discrete problems in string theory by some continuous approximation that might actually be a very bad example of the real problem, and might actually put you in a situation where the continuous problem is just much easier than the potentially NP-hard discrete optimization problem would be. So you guys were able to find solutions. There are ways to try to do discrete optimization in this context, but I think you guys simply are not doing continuous fluxes. You're just doing optimization on discrete fluxes, right? Yeah. And these constraints are hard to satisfy, which is why you need these sorts of algorithms. A brute force scan of discrete fluxes in a high-dimensional flux space is simply, the probability that it finds a solution is very low, which is why you need stuff like this. It's a great point, and it's a rather general point, these discrete versus continuous problems. Anyone else? So I'm going to tell you about two themes in a little bit deeper look. One is what I'll call auto-diff everything, and the other is a little bit about flows. So auto-diff everything is a slogan for differentiable science, and I'm getting more and more messages. A theme in ML, this is a theme in ML since differentiability opens up new algorithms and analyses. And here there's a pipeline for 2B flux vacua. So auto-diff everything. I said to GPT, write me 2 sentences explaining the basics of the slogan auto-diff everything in the context of differentiable science. Be clear why it's interesting and important. The slogan auto-diff everything in differentiable science advocates the widespread use of automatic differentiation, which is an ML thing, a method that computationally derives precise gradients of complex functions. This approach is crucial as it enables more efficient and accurate modeling in various scientific and engineering fields, significantly advancing research and development through improved optimization and analysis. So that's all true. The big idea is that many more things than you think are differentiable. Obviously, simple differentiable functions are differentiable. But by composing those simple differentiable functions into a huge neural network, the reason ML works is because people have differentiable neural networks that they can optimize with gradient descent. And more generally, in certain complex simulations, you build up a computational graph that you can differentiate through. So in particular, numerical solutions to ODEs, if you keep track of the updates, build up a computational graph that you can differentiate through. So, OK, good. In the interest of time, there's ways to do this in molecular dynamics and in cosmology. I refer you to these papers. But one way to do it is using something called JAX. And this is something that people did with flux vacua. So JAX is a Google package that is basically a differentiable version of NumPy that has a number of nice features that speed up calculations and make differentiation very automatic. So for example, just-in-time compilation converts functions to machine code at runtime, and this can give pretty big speedups in the code. And there's some analyses of this recently. Various other aspects make vectorization automatic so that you can implement across many CPU cores. The basic takeaway message is that you want to use some of the libraries that have been developed by professionals in industry because people have thought very hard about how to make differentiation fast, how to make code faster by doing just-in-time compilation, and so on and so forth. So in a paper this summer, Sven and Andreas and Dubé came up with a package that is publicly available, right? Not yet? Will be? OK, good. Is going to be publicly available called JAX vacua that takes some sort of Calabi-Yau orientifold, some sort of model construction, and pipes it into an EFT module that does automatic differentiation to get from the pre-potential to be able to get the scalar potential associated with flux vacua. They have some sort of sampling module, which is why I raised Andreas's answer to Jonathan's question, some sort of sampling module for sampling flux vacua. Given those fluxes, they then need to write down the scalar potential and minimize it, and then they have some sort of filtering that they can truncate on various things that they care about. So this is a very nice pipeline that uses one of the most popular libraries that's good for many reasons, including this autodiff, this just-in-time compilation, and the automatic vectorization. And this is something that they did in 2B flux vacua. So there's many different things that you can take in here, but in particular, this is something where you guys are using the Calabi-Yau tools Kreutzer-Skarka package and pumping it into this full EFT module to get honest-to-God flux vacua at the end of the day, stabilized complex structure, et cetera. Good. So maybe on this slide, the key thing to mention is that they have a way to go from Calabi-Yau data directly to prepotentials hard-coded, but then they use autodiff, as I understand it, the differentiation that's built into JAX to go from the prepotential to EFT. So the exact derivatives are built in there. There's no numerical derivatives, and they're not hard-coding the potential. They're hard-coding the prepotential. Finally, when you look at some of the results, I mean, you can see for various values of H11 and H21 and associated D3 charges, they are getting millions or hundreds of thousands of vacua, depending on the setup. Of course, as the number of moduli goes up, the difficulty of this problem is also going up for a number of reasons, including the dimensionality, the difficulty of the optimization, et cetera. But you know, this is adding these up. This is order 2 million flux vacua. Thank you. And Andreas can tell you a little bit about a bit more about this. And in fact, here he is. And on this and many other things, he says, "Ask me. I know way more than Jim." So please, I advertise grilling him about this because it's exciting work. Finally, I want to tell you about Calabi-Yau metrics and a little bit about neural network theory. So we know, I cannot emphasize enough, we know 0 non-trivial compact Calabi-Yau metrics. Okay? So that is something that we do not advertise because we might then get very hard questions from our condensed matter colleagues about, oh, you don't know the most fundamental object on your manifold? What are you doing? We would tell them something about SUSY and calibration and what we can do even though we don't know the metric, et cetera. And that's all very good. But we know 0, and modeling them with neural networks, which we'll hear about next, gives state-of-the-art results. So in this context, what I want to ask is, the training the neural network, which drives you towards the Calabi-Yau metric, corresponds to some sort of geometric flow in the space of metrics, and it encompasses some famous results in mathematical physics. And so I want to give some sort of theory underlying these compact Calabi-Yau metrics. So since there's a whole talk on this next, I will just say that what our friends so brilliantly did is they said, let the neural network be the metric. The reason this is a good idea is because neural networks are very, very good function approximators. So somewhere in that neural network space, there's something very close to the Calabi-Yau metric. That is absolutely what they find in practice. 15 minutes with a neural network, depending on details, it would cost you about 30 years with Donaldson's algorithm for numerical approximation. This is also the same sort of thing that condensed matter physicists do with ML in the context of finding quantum many-body ground states, which is also a very hard problem. OK, good. So what's happening is that there's some Calabi-Yau metric that we would like to know so that we can do physics that we haven't been able to do before. At time 0, there's some initial neural network that's very far away from the Calabi-Yau metric, and you follow the gradient of some scalar functional L, and you do gradient descent to try to arrive at the Calabi-Yau fixed point. This is what Magdalena's talk is on. If you were to restart your code and use a different random seed, you would start somewhere else in metric space, and you would find a metric flow towards the Calabi-Yau fixed point. And you could restart your code again and find another metric flow towards the Calabi-Yau fixed point. But very famously, flows in the space of metrics is something that mathematicians study. This is Richard Hamilton, and this is Alexander Hamilton. But Richard Hamilton, in the 1980s, developed something called Ricci flow. And when I first started telling people about my friend's brilliant work, I often got the question, how do these neural network metric flows that converge to Calabi-Yau relate to Ricci flow? Because Ricci flow is a fixed point of, the Calabi-Yau metrics are a fixed point of Ricci flow, just as whatever is happening here. When you look at this, this is the gradient of a scalar functional. This on the right-hand side does not look in any obvious way like the gradient of a scalar functional. And so a priori, until we thought about it harder, we just realized that these things probably are very different. But actually, Perelman's work in the 2000s that was one of the first steps that led to him proving the Poincare conjecture, is that he showed that Ricci flow after a time-dependent diffeomorphism is the gradient of a scalar functional. So there's a version of Ricci flow that fits better into this story. And so okay, so there's some result from neural network theory called the neural tangent kernel that makes things rather tractable. This is the object. This is sort of one of the fundamental objects that governs, from a learning perspective, what is happening in the context of these updates. So what we did recently is to take this ML theory and to, in the case that the neural network is not some scalar function f, but is representing some 2-index tensor, some metric g, we applied this theory in the context of metric flows to be able to come up with a theory of metric flows. And in general, what I would emphasize is that this bit of the story here is the general equation that would come from any neural network. In a certain infinite width limit, this object theta, which in principle is very complicated, it involves a sum over all of the parameters, and generally there's like hundreds of thousands or millions of parameters. What the main ML theory result is that this object in a certain infinite width limit becomes very tractable, and it becomes, in that limit, a computable fixed function that you can just compute once and for all. And what that means is that you can then simplify the dynamics significantly. You can and then sort of start to ask the question: can we relate this to Perelman's formulation? So Perelman's formulation of the Ricci flow involves the gradient of some scalar functional that's effectively Einstein-Dilaton theory. The neural network metric flow story is up here. And what we were able to show is that there's ways to make architecture choices and loss function choices that realize Perelman's formulation of Ricci flow exactly as a neural network metric flow. So do some architectures yield Perelman's result? And the answer is that it does. One crucial thing that you need to do is induce locality in the flow to collapse this integral via a delta function into something with local updates. But there's all sorts of technicalities I can mention. But the punchline is that we know how to realize Perelman's story in that context. And I lost my slide. Huh?
Yes, so
Okay.
talk is over. Oh, thank you very much, Tim. Yeah, so the warnings you were getting is actually the light bulb needs to be replaced. So this means that the talk is actually over now. The lamp will be replaced, and we take questions now. We do the coffee break.
So I have a question. Thanks for the great talk. I had a question about the convergence of the neural network flow. So you have a kind of, I think, a guarantee that it converges to something, but in the context of other neural networks, often you hit like a local, extrema or something like that, and there's no guarantee that the loss function is kind of converging to the absolute minimum across the entire landscape of weights. So what's the guarantee here that you actually hit the honest to God Calabi-Yau metric and not just something that's rough approximation of it?
Yeah, that's a great question. So first of all, on the local minimum question, one thing that various optimization techniques, including stochastic gradient descent, is in escaping those local minima. But that doesn't guarantee that you get all the way to the global minimum. So there are two comments there. One of them is that in practice, what people are finding is that they're getting way better gains in the losses than anyone's ever gotten before. And then when they do physics calculations associated with that, the physics intuition that they get is matching. The physics intuition they have is matching what the metric gives them. So that is like a physics proof in quotes. But in principle, what you would really want, this is in principle some solution that is supposed to be nearby, in air quotes, to the actual Calabi-Yau metric. And what a PDEs person would do, and what PDEs people actually do in different contexts, is they use a neural network to find something that's close to the right solution. And then in certain cases, there's someone at Brown named Javier Gomez Serrano. He takes an approximate solution to the PDE, and then he can prove some theorem that there's something close by that actually does that. We do not have that in the Calabi-Yau case, and if someone learns how to do that, that'd be very important.
But I guess the counter could also be that maybe I don't even care about the exact metric. If I can calculate the Euclides or whatever,
Yeah.
approximation, who cares if I had it?
I mean,
Would that be fair answer?
yeah, good. I mean,
That's the
if,
physics answer.
that is definitely the
Yeah,
physics
that's it.
answer.
All right, fine. I didn't find any real metric, but I don't care.
Yeah, if it's 1% from the multiplet metric, what you
Yeah.
can.
Absolutely, particularly in cases where you can do some physics calculations that you couldn't do before, and it makes sense and matches intuition. So there's a paper by Fabian and Ashmore on level crossing of KK modes as you move into the moduli space, and you know, maybe this is further from the Calabi-Yau metric that we want, but it's sort of matching intuition. You know, there's various towers doing various cool things. Certainly from the point of view of rigor, like at a math level, it's not there. Yeah, who knows?
Hi, thanks for the talk. So when you talk about the Ricci flow and the comparison with the neural network,
Yes.
are you using the Perelman's functional as a loss to get that, or?
Yeah.
Okay.
Oh wow, I got my slides back. Great. So huh? Okay, good. Well, yeah, good. So the one crucial step is to pass from here to here. You take an infinite width limit, and this object that is basically impossible to do anything with becomes perfectly tractable. And then you make architecture choices to induce a delta function and kill the mixing between the components here. And that moves you to what we call a local metric flow. Now you're in a world where it's starting to look like Perelman. And then there's some remnant piece of the MTK, and you basically have to choose the loss function to be Perelman's functional over that thing, and then you get Perelman bang on. So the crucial step is, first of all, in getting locality and killing component mixing to get to what the sort of thing mathematicians consider. And then you need a loss function choice, which is Perelman's function.
Okay, thanks.
Wait for the microphone.
But can you, now that we have this back, can you tell us something about the Bayesian story that you're going to tell us?
Bayesian story. Good. I can. I will be super fast here. Random matrix theory is a very interesting idea. This is part of my dreams section. What people have done is draw random matrix ensembles and have them be toy models for Lagrangians. From a machine learning perspective, this is what we would call an untrained generative model. It generates toy models for string data, but it wasn't actually trained on any string data a priori. And so what one would want to do is do some sort of ML training to come up on string data to come up with some generative model for string data that simulates string data. If you had such a thing, this is a very baby step paper that we had a couple of years ago that was like an in-principle proof of the idea. But if you had that, what you might then imagine doing is doing some Bayesian inference. So the method by which we update data to update, we use data to update our belief in a model is statistical inference. This is actually the most famous work by Witten, the best cited work by Witten. It's his daughter, not Edward. And in strings, you might imagine a statistical pipeline for this. So this is all very futuristic, but what you might imagine is that you use ML-based methods trained on string data to draw from some approximate distribution on string data, ideally the full cosmological measure. You would then use string techniques, traditional things to compute observables, and use something called simulation-based inference to compute the data-conditioned Bayesian posterior. This is the sort of thing that is the right way to do Bayesian inference. And then you can make predictions in the posterior. So simulate string theory to get draws from the prior, use simulation-based inference to get the posterior that's conditioned on data, and then see how the posterior makes different predictions from the prior. Finally, I do think it's worth mentioning that Jonathan has this nice paper. A concern that he raised here and in conversations that we had some time back is even if you can do all this, there's a fundamental concern, which is from statistical learning theory, there's just a question, given a statistical model, how much can you learn about the full theory, that is the UV data, from a finite number of IR experiments? And so that's a learning theory question, and he probably has much more to say about it than I do. But this is the way that I might imagine doing Bayesian inference. And what Cody and I did was a very first baby step on step one, but one could try running the whole pipeline.
So step one, it would be like addressing the measure problem with it.
Good. So you could imagine sampling from any prior here. So if you could simulate from some prior that someone else comes up with, you could do the whole thing, and then it would be conditioned on the prior that you drew your string data from. What you really want to know, in my opinion, is the correct cosmological measure on string vacua That's a very loaded, hard to compute, hard to understand thing. But if you had that, then you would want to come up with draws from that measure and then run the standard Bayesian inference story. And I think that one of the points of that is that if you were able to simulate that, if you were able to have an ML method that would spit out Lagrangians drawn from the right measure, then you would just study the appropriate statistics of those Lagrangians and see if it matches data. So yes, if you had the oracle back and he could tell you the measure, you would want it and you'd want to learn to do that. But well, I think we're many years from that.
Yeah, maybe a general question. What do you think about demonstrating swampland conjecture with these techniques? Like, for example, the distance conjecture.
Good. So I think, I'm forgetting the details, I think Nana Cabo-Vizet wrote a paper about that a couple of years ago, maybe not the distance conjecture, but I've been trying to emphasize that sampling is important. Many swampland papers come up with a conjecture and draw a line for some inequality, and then populate some points from string theory and say, look, it's all below the line, right? But what you would like to be able to do if you ML'd it was come up with some ML technique that learns adversarially how to sample string data that is increasingly close to violating a swampland conjecture. So if your line is here and your samples generally come down here, you would like to have some sort of ML technique that tries to drive you towards the boundary. And then if you're doing tons of sampling right here and you really can't get over, it lends some credence to the idea that it's really a theorem. And if you get over, then you either need to modify your conjecture or throw it out. But I think there's only been one paper on that, and it was some time ago.
Thanks.
Sorry, this will have bias towards the data that was trained on.
Sorry, in the swampland case?
Yeah.
Yeah, that's
Because the whole
that's
point
absolutely
there is
true.
more generalized. Because if I kind of already know that in that case it's true, then how am I going to beat it if the things that I already know? It's kind of like a loop.
So one of the reasons that it's not just a loop is that something that you can do is that you can iterate your training many times. And in the training, you can build in a notion of how far you are from the boundary. And you can do something called active learning, which is to systematically over time add more and more training data that is closer and closer to the boundary. So in some sense, exactly what yes, there is an initial bias, but what you're really trying to do is to bias the model to learn to draw from as close to the swampland boundary as possible. So it's basically built into the learning algorithm. And to avoid the loop that you're worried about, I would say what you should do is use active learning and add to your training data the examples that are close to the boundary, so it biases in that direction.
I'd say in the interest of time, we continue over coffee and we meet back at 11:30. And that's thank Jim again.
Thank you all.
Coffee's outside.
Yeah, but that's, I mean, I'll just look at when you wave. Yeah, sure.
All right, welcome back from coffee to the second section. And we're very happy to have Magdalena Lafos from Uppsala, and she'll talk about machine learning Calabi-Yau metrics.
Thank you very much. So I will try to speak loud so you can hear me in the back. Can you hear me now? Could you just wave a bit? Okay, good, thanks. So I will talk about follow on where Jim left off, basically, and talk about a particular problem in string theory where machine learning has been applied in recent years, and that's to learn Calabi-Yau metrics. So this is the problem is to learn the Ritchie-Flat metric on a Calabi-Yau. And this is based on work done in collaboration with André Lucas and Fabian Rulli, who are here, and Robin Schneider, who was a PhD student in Uppsala, and Jakob Hendy and Moritz Wange, who are present PhD students in Uppsala. And there are 2 papers related to this and some work in progress. And during my talk, I will also touch upon work that has been done by many other groups. So we are not the only one working on this. It's a big, interesting topic to work on. And I hope also in the discussion or in the questions afterwards that if there are some things that are left out, that maybe some of the experts in the room can fill that in. So there's an alternative title for my talk, which is that with very simple machine learning techniques, we can learn Calabi-Yau metrics. So the slogan that I'd like you to take home for this is that we don't need to go very advanced in machine learning to actually resolve some of the issues we've had in theoretical physics. And that's rather surprising. Maybe that is hinting at something in the Calabi-Yau geometries that we haven't appreciated so far. So it's a good message to take home. Why is this? Why does these simple methods work so well? And can we learn something from it? So let me set up the problem and motivate why we want to do this. So we're, from the context of complexifications of string theory and the swampland, the Calabi-Yau geometries have a special place. So they are very popular in these constructions, and the reason for that is that we know a lot about Calabi-Yau manifolds. In particular, we know a lot about the topological properties from algebraic geometry, and we can construct examples. So they are very non-trivial geometries where we can still construct concrete examples and we can compute things in detail. The topology and the geometry of the compact dimensions in the string compactifications is always key to the physics that we observe. And we've heard something about that when we talked about in the conference so far. So in the swampland setting, for example, the swampland distance conjecture, which we've heard about how we can test it in the Calabi-Yau moduli space, is something that is we can explore using once we know more things about the geometries that we are looking at. So the Ritchie-Flat Calabi-Yau metric then that is the topic of this talk has the information about it has a lot of information about this compact geometry and where it's how we can measure distances on the geometry, what kind of curvature it has, and what masses and so on we get for fields in string compactifications. So the question that we want to ask then in this talk is, can we compute it in examples? And it's important, since yesterday we talked a lot about very general results in the swampland setting, to remember here that we are working on examples. So we're doing very specific computations on specific geometries. And this is so that we can use these machine learning techniques and do numerical computations. So in order to do something like that, then we need to construct our examples. And there are huge databases of Calabi-Yau geometries available that we can use. And the thing that we are drawing on in these machine learning implementations are constructions of Calabi-Yau geometries as some sort of hypersurface or intersection of hypersurfaces in a simpler ambient space. So given this simpler ambient space, we can compute certain things, and this allows us to make progress on the Calabi-Yau metric problem. So a particular geometry that is very important is the quintic. So the quintic is given by a quintic polynomial in an ambient space, which is the complex projective four-dimensional space, P4. And this is one of the geometries that is collected in the CC database. And so this is a simple and kind of simple geometry that is kind of like the it's the favorite example where most of these numerical methods have been tested. What has happened in recent years is that we now we have evolved these numerical methods and we can apply them to more advanced settings, so to any kind of generalization of the quintic in the CC space, so where we replace the ambient space P4 by a Cartesian product of projective spaces. And we're looking at various polynomial equations in this ambient space that give us a complete intersection Calabi-Yau. Or we can exchange the ambient space and look at these toric ambient spaces instead. And that, in particular, can be done if we're looking at the Calabi-Yau manifolds that we get from the Kreutzberg database of toric varieties. So the problem we want to solve is that we want to find the unique Ritchie-Flat metric on the Calabi-Yau, and we know that this exists from the Calabi-Yau theorem, which is stated here. So if X is an n-dimensional compact complex Kähler manifold with vanishing first Chern class, then we know that in any given Kähler class, X will admit one unique Ritchie-Flat metric, which is the one that we're looking for. The problem is, of course, that in proving this, this metric was not constructed. So we don't have an analytic expression for the Calabi-Yau metric, as Jim was mentioning in his talk just before the break. And also, if we would want to just try to solve for this and say that, okay, I want to find this metric, I want to solve the condition that the Ritchie tensor should be 0, then this is a highly non-trivial, non-linear PDE. So it's a very hard mathematical problem to solve. Of course, since we are in the Calabi-Yau space, we know a lot more, and this is goes back all the way back to the work of Yau. So one thing we can say is that if we want to stay in the same Kähler class, then and find the Kähler metric there, then that corresponds to looking for a Kähler form in that Kähler class. So something that is related to some reference Kähler form by adding an exact piece. And we can write that exact piece as del bar of a function phi. Then the second realization of Yau is that we can rewrite the condition of being Ritchie-flat as this Monge-Ampere equation here, which is saying that once we have found this Kähler form that we're looking for, that gives us the Ritchie-flat metric, then if we wedge that 3 times, then that will give us a volume form. And there is also another way of constructing a volume form in a Calabi-Yau, which is by using the holomorphic top form of the Calabi-Yau. So this is called omega here. It will be a 3,0 form on a 3-dimensional Calabi-Yau. And if we wedge that with its complex conjugate, then this will also give a volume form. Now, since these two are volume forms on the Calabi-Yau, they need to be related by a constant, or they need to be related in this way. They need to be proportional. And this kappa here has to be a constant, basically because of uniqueness here. So what we see here is that from this reformulation as a Monge-Ampere equation, we can translate this condition of Ritchie flatness into a second-order partial differential equation for this function phi here. So this is an immense simplification of the problem and something that is essential to the implementations that we will talk about. So very importantly here, once we have constructed our Calabi-Yau example, we can compute such a reference Kähler form, and we can also compute this holomorphic top form. And this is known how to do this from the way that we construct these geometries. And I will not go into the details in the short time that I have today. But importantly, we can compute them. So we can then set up the problem, our numerical problem, say that we want to solve this Monge-Ampere equation, yeah? And we want to do this numerically. So what do we need to do then? Well, we need to sample points, random points on the Calabi-Yau, where we can compute these reference forms, the reference Kähler form and the holomorphic top form. So we compute all those, and then we solve the Monge pair numerically using some numerical method to do that for the Kähler form that we're looking for, or for the function phi, which is related then to the Kähler potential. And then we check that the solution is good. So we check that the Monge pair equation holds and that the Ricci tensor is 0. So this is the strategy that is employed then in any kind of numerical method. So this is a long-standing problem. It's been around since Calabi-Yau manifolds were invented. And there have been different numerical approaches to solve this problem. And this is a list, a non-complete list of references. So Jim mentioned the canonical method, which is called the Donaldson algorithm, which is the first, which is a nice and very mathematically well-controlled way of solving this, but that is computationally slow. And then there are other approaches that have been employed to this. And what we're focusing on today are these machine learning approaches. So one important thing to say in this, related to these more recent developments, is that if you're interested in this and if you want to apply these machine learning methods to your own setting where you have some problem where you want to compute the Calabi-Yau metric, then there are packages that are available. And these packages are open source. They can be manipulated to do what you want to do. And all of these, so they are available and you can use them. And it's also highly encouraged to contact the authors of these packages and have discussions about what kind of modifications can be made. Because it may be that you're interested in some particular situation where you don't really need the Calabi-Yau metric, but you need some modification of it. And then starting from these packages might give you a lot of leverage in reaching that goal. So that's a bit of publicity. I've been working on this middle package here, CY metric, which is the one that I will talk about in this talk. But the other ones are equally interesting packages, and they differ in some details that I might touch upon, but if you're interested in that, you can also ask me in the break. Okay, so since this is a long-standing quest, let me say something about the different approaches you can take. So there's basically two different approaches that I like to highlight. So one is where you do something that is that was pioneered by Donaldson in his algorithm, which is that you focus on the Kähler potential of the metric that you want to learn, so the Ricci-flat metric, and you look for solutions. So you look for such Kähler potentials that fall into a particular class, which are expanded in a particular basis of homogeneous polynomials. So the important thing is here is that you can choose a degree of these polynomials, and that will give you a finite basis. And then you expand your Kähler potential in that basis. And then you can apply different numerical techniques. So in the Donaldson algorithm, it's a fixed point iteration scheme. And you can also write down a functional and minimize an NAD functional and minimize that. Or you can employ machine learning to look for these parameters here in this matrix H. However, as we heard in the last talk, machine learning and neural networks give you a different way of approaching this problem, using that neural networks are universal approximators. So you can alternatively, instead of writing down this particular ansatz for your Kähler potential, you can search for this freely using a neural net. And what you do then is that you set up your neural network, much in the way that Jim talked about in this last talk, and then you train it in order to minimize some loss that is related to the conditions that you want to satisfy. And this is what I want to detail now. So the machine learning implementation in that case is then that you have your point sample, and this will depend on the moduli of your Calabi-Yau. So the moduli and the points are sort of your input to the machine learning model. This machine learning model is some sort of neural network, has some particular architecture, some nodes that are connected. And this will be optimized using a training algorithm so that the loss function is minimized. So this is an optimization problem. Then this will give you a prediction for the metric, and you have to check that this metric makes sense. And there are error measures that are used for doing that check. So I will talk about this particular implementation, which is the CY metric package. And here are some brief summary of what this is. So this is a package. It's written in Python and Mathematica So it has two interfaces depending on your what you like. And it decomposes into two pieces. One is a piece which generates the points in your sample. So we need to sample points on the Calabi-Yau. This is a non-trivial problem. And this is something that you always need to do in these implementations. And then there are these neural networks that give you the Calabi-Yau metric. So let's talk about the point generators. So the first thing we need to do then, in order to have the points, is to think about what we will use them for. So one thing is that we will use them as input to the neural network, but we also want to use them in the end when we check the performance of our approximation. So we want to compute some error measures. And these error measures are defined here. It's called the sigma measure, which, as you can see, is a measure of how well we are fulfilling our prediction, J prediction here, is fulfilling the Monge-Ampere equation. And then there's the Ritchie measure, which is checking. It gives us one measure of how far we are from being Ritchie flat. And these measures here are integrated over the manifold. So we want to see how we're doing globally on the manifold for these measures once we're done with the training. So in any numerical implementation, if we're computing integrals, we need to do that we need to trade the integral for some sort of summation. So we do this with Monte Carlo integration. This is also standard. These kind of error measures and the way of computing these integrals is the same way that we do for different numerical methods. So it has nothing to do with machine learning. But when we generate points, we want to be able to compute such integrals, which means that we need to sample points with respect to a known measure. So a point generator should give us a sample of points that are randomly distributed over the Calabi-Yau, and this distribution is with respect to a particular measure, so a particular metric on the Calabi-Yau. Now, we don't know the Calabi-Yau metric, so when we start, so we take this reference metric, which I will refer to as the Fubini-Studi metric, because that's what it is, and this will be the measure that we sample with respect to. So there are methods to do this. There is a well-known method for which was developed for the quintic, where you use certain properties that are given by this mathematical theorem by Schiffman and Saldich that tells you that if you sample points in a particular way on the ambient space of the Calabi-Yau, so here the P4, then these points that you sample on the P4 will be distributed with respect to the Fubini-Studi metric on the P4. And if you sample two such points and connect them with a line, then this line will intersect your hypersurface in a number of points. So here we have a quintic hypersurface that will be 5 points. So you do this many times, and then you get many points on your Calabi-Yau, and they will be distributed with respect to the Fubini-Studi measure on your Calabi-Yau. So if you restrict your Fubini-Studi measure on the ambient space to the Calabi-Yau. So this is all very good. So you have your sample of points, and this can be generalized. So it can be generalized to all manifolds in the CC database, and we generalized it to all Calabi-Yau hypersurfaces in the Kreutzer-Skarke database. How am I doing with time? Okay, then I will skip the details of this implementations, and I will tell you something about the machine learning bit. So basically, the point sampling is solved, and it relies on in particular on the Schiffman-Saldich theorem. So the machine learning implementation in CY metric is one of these free implementations. So we're not expanding the metric in some particular, or the Kähler potential in some particular basis. Rather, what we do is the following. We input the moduli and the points into a neural network. This neural network consists of a number of fully connected layers with some nodes. We go from one layer to the other by this affine transformation that we recognize from Jim's talk, and then we have a nonlinear addition to that here. And then in the end, we output either the metric or the Kähler potential that we're looking for. So there are a number of choices here when you set this up. So you can choose how many nodes you have in different layers, how many layers you have, what kind of nonlinear functions you have, and so on. You can also choose what you want to encode here. So if I want to predict the Kähler potential, then I have already told I have already included that this is a Kähler metric that I will get out of this Kähler potential. Whereas if I predict the metric freely, then I'm not guaranteed that this is Kähler. So if I, depending on those architectural choices regarding to the network, I will need to include loss functions that will encode the other constraints. So in CMY metric, there are a number of different, more or less free ways of doing this. So ansatz, say for the metric, that looks something like this. So either you use the network to predict the full metric, or some addition to this reference metric that we have, the Fubini-Studio metric, or you can go to encode that this should be Kähler, and then you have the most constrained architecture here for the network. Okay, so then you have your network, you have your parameters, they are initialized, and you want to train it. So in order to tell the network where it should go, you need to tell it what kind of constraints it should fulfill. So here, because we don't know what the Ritchie-Flat metric is, we cannot use supervised learning. We have to use semi-supervised learning when we are defining these custom loss functions that encode our mathematical constraints. So for example, for the Monge-Ampere equation, we write down a function which is checking how well we are, so how the volume form that we get from the metric is comparing to the volume form that we get from omega wedge omega bar. And then we can compute this with, so we're doing this over a number of points, and we're taking some of the norms of these. And we can do this with some different, giving different weights to different points, which is also a bit of choices related to that. Then if we have one of these freer metric ansatz, we also need to have further losses. So we need to have something that encodes that the Ritchie tensor should be 0, that the metric should be Kähler, that the metric should be transformed in the right way as we go from one patch to the other. We're doing this on a manifold. We need to check that the metric that we get is global. And also something if we're training on more complicated or more advanced Calabi-Yaos that have more than one Kähler parameter, then we need to check that we stay in the same Kähler class, and that needs a Kähler class loss. So we set this up, we have these loss functions, and then we can do the training. And after we train, we then check with these benchmarks. So then we check that we're doing the right thing. And if we are working on a Calabi-Yau with more than one Kähler parameter, then we also need to check again that we stay in the same Kähler class. And this requires checking, for example, that the volume stays constant and that certain topological quantities that are related to the Kähler class also stay constant. So let me show you some experiments in the last minute that I have, and then we can open up for questions. So one thing that has been a bit of an issue for example, the Donaldson algorithm is that you can do very well on, since you're relying on this expansion in a polynomial basis, you can do very well if you have a lot of symmetry in the problem so that you can reduce the number of elements you have in this, the number of parameters that you need to learn in this emission matrix HAB that I showed you some slides ago. However, with machine learning techniques, these free machine learning techniques, this is not really an issue. So we can train for the quintic on something that is highly symmetric, like the Fermat. It has a lot of discrete symmetries. And we can train on something that is just completely generic when it comes to complex structure moduli. And we see that, sure, it's faster to train on the Fermat. We reach lower levels of these loss functions during training and of the error measures that we check afterwards. So they are here. It's a bit tricky to see the scale here, so I'm sorry for that. But basically, training results in better approximations on the Fermat. But training also works on this non-symmetric Calabi-Yau. So the methods work. And we can look at more complicated example. This is a particular Kreutzer-Skarke example. Training works here as well. The losses go down, the volumes stay constant, the sigma measure goes down, the Ritchie measure does something funny at the beginning, but then it goes down. So training works also for more complicated Calabi-Yaus. So I will skip the further developments and go to the conclusions. So the main message is that with these simple neural networks, we can learn Calabi-Yau metrics. we can do so for a wide variety of Calabi-Yau manifolds. The name of the game in this free implementation, this kind of architecture that we have developed, is to encode the mathematical constraints in loss functions. Now, this is a choice one can make. How much do we want to encode in the architecture of the neural network, and how much do we want to encode in the loss functions? And there are pros and cons with these different choices, and there are different developments in the literature where this has been discussed. So there are places that one would want to go in the future. So one thing is that with the CY metric package in particular, we can compute the Calabi-Yau at a given point in moduli space, but it's just computed at that point. So if we want a moduli-dependent Calabi-Yau, then we would need to do something more. And there are some developments in the literature. Fabian and Sven and others have worked on this, and in particular for simpler Calabi-Yaus like the quintic. So there's there's also this discussion about what kind of architecture should you have that makes it easier or less easy to learn the modular dependence. Then, of course, applications in physics is very interesting. And also going beyond the Calabi-Yau case to look at other kinds of geometries is something that one could surely imagine to do in this setting. Okay, and I'll stop there. Thank you.
Thank you very much, Magdalena. Questions, Thomas?
Yeah, thank you. Thanks. It's about the applications in physics. So Yukawa couplings are an example of physical data for which you actually need to go beyond, well, you need to know the metric a bit to compute. But say other physical data is often, I mean, an example is, say, if you do conformal Calabi-Yaus, then the Monge-Ampère equation will be, there's another one, which is related to the warp factor equation. And I think, I mean, that seems an important one because there's lots of discussions about how you glue a throat into a compact Calabi-Yau and what happens at the gluing. Do you think this is feasible, or is that a little bit beyond? Because that's a double, I mean, then you have two equations.
I think it's certainly something that one should attempt. I have not looked at the details, so I don't know if it's feasible, but I definitely think one should attempt it. So Andre made a very good comment yesterday in the discussion that if you're looking for something that is only going to affect a very small portion of the Calabi-Yau, it might be hard to detect it with these numerical methods. So maybe you need to sample points, over-sample points in that particular region in order to see this. So, but
how do you measure small?
Yeah,
because you see, for warp throat, it can actually dominate the volume.
Yeah, so I think it's definitely a very interesting problem to look at. Yeah. And if there is, I mean, given, like in this case we had the Monge-Ampère equation. So given such equations, one can certainly, set up an architecture that goes and looks for solutions for those equations using a stochastic gradient descent, which is what we're using. Yeah. So we're training the network with some optimization routine, and then one can attempt to look for solutions for different equations. And what this corresponds to is that you need to change your loss functions that you have. So these loss functions that you have here would then need to be updated with the equations that you want to solve. So that's basically what you want to do.
Just a quick follow-up to Thomas' questions. When we include the warp factor, you also have to include the brains. And how do you take into account the...
I don't. So short answer, I don't know. And it's maybe one should excise them in some way. But I'm just speculating here. I haven't really thought.
As a comment, it depends a little bit what you want to do. If you want to, for example, reduce metric on the brain, you could get that.
Yeah.
If you know where the brain locus is, that's perfectly possible, because unlike discrete methods, the neural network will give you the metric everywhere, including where the brain sits.
Yeah. That's a very important point. So I didn't really talk about that here, but we are training the network in certain points, and then we are testing it in other points. So we are checking that the metric that we learn is not only true in the points that we have sampled on, but it also interpolates, or it works in other points. So it does give us some global information.
Okay. No. Okay. Yeah. So thanks. So regarding some of the physical applications, my question was like, how easy would it be like to compute the moduli dependence of the first KK modes? Because usually we have like some results regarding like the very excited states, but in some sometimes what might be interesting for us is like the first ones, which are like the ones that might not be like as homogeneous spaces, or like you don't have bias asymptotic formula or some mathematical results that tell you how they go. So how easy would it be like to get moduli dependence of the first excited KK modes?
Yes. So the person to talk about this is I think maybe Fabian. So that I just wanted to talk about these works in relation to your question. So looking at the massive modes on Calabi-Yau manifolds using numerical metrics is something that has been done. And so these papers by Anthony Ashmore and Ashmore Rula and Ahmed Rula and Fabian and collaborators, they are looking at exactly that on the quintic and using the moduli dependent metric also in one of this. So this is something that you can do, and you can see very interesting behavior of these massive modes and how they change as you move in the moduli space. So this is something that you can do, and I would just direct you to these papers. So these are papers from Ashmore and Ashmore Rula and Ahmed.
Okay, thanks.
And maybe Fabian, if you want to comment.
Thanks.
We're running behind.
Yeah,
so.
sorry.
Thanks for that very nice talk. I had two questions. One question: for your point sampling, as you start from the Frobenius 2D metric and approach the Richeflat metric, do you adapt? So
the points are sampled with a known measure.
Mm-hmm.
And then when we are computing, so when we're using those points for computations in various places, particularly when we're computing these error measures, then we are correcting for that by computing, for example, integrals as these weighted sums. So those weights here, so we know the Calabi-Yau measure because we can. That's given by the omega wedge omega bar. So this is something we know. I can compute, and then we sample with respect to this measure. So this is something we can compute then from the reference Kähler form. So this is something we compute then in every point. So we have this information, and whenever we're computing something, we're using that way.
So assuming you have enough points to begin with, then it's going to work.
Yeah.
Thanks. Second question: can you, as an application, can you start finding minimal surfaces in a given homology class if it's not calibrated, for instance?
I think that's a very interesting problem to look at, and I would say yes, but no one has done it. So I think it's but really using the metric to compute the volume of a cycle is something that you can do, and then you can look for how you could adapt the metric so that the volume becomes minimized. So it's not a problem. I don't think anyone has really worked on that. Now I'm looking at other people.
It's very natural. So how to sample the submanifolds.
Yeah. So it's the sampling of sampling of submanifolds is something you need to think about first. Once you have that, then.
Yeah, I guess
Thanks.
in my cases where you don't have a calibrated representative.
Yeah, exactly. I guess you could test it first with calibrated ones, but yeah.
Very important non-supersymmetric physics.
Okay, I don't see any further questions, so let's thank Magdalena again.